Okay, so the reason we have been talking about significant figures is we know that the last digit is uncertain because it's associated with Merriman errors. And the Merriman errors could be random errors or systematic error. So here we're going to talk about, like in concept, what's the difference between these two types of errors. I'll give you two examples. The first example is, let's say we have a pH meter. And for pH meter, if you want to make sure that it's ready to use, you have to do calibration first, meaning that you will have to use 3 different buffer solutions that have pH of 4.00, 7.00, and 10.00. So 3 calibration solutions, and you will try them individually to make sure the value will match with the with the value on the label. Now, for example, in this case, when I'm using the pH meter to measure the pH 7.00 buffer, I get a reading of 8.05. Okay, so the reading is definitely higher than the desired value, which means that there's some problem with the measurement, right? I'm not going to talk about what type of error it is now, but let's look at the next example. So the next example is when you have let's say in this case you have a ruler, and it's not a ruler, but it's an indicator of a measurement of absorbance. Okay, so the reading here, the absorbance is showing to be here, and you have to read from the scale what is the percent transmittance. The absorbance has similar meaning of percent transmittance. There's a conversion formula which we will be talk about later in the semester. But now let's just look at the percent transmittance. Can you go ahead and type your reading of the percent transmittance in the chat box? While you typed your answer, you can go ahead and look at other people's answers there and think about it. So we see numbers all the way from, let's say, 58.1 to 58.5, right? So far, and 6. Okay, I see 6. 7. Yeah, so we see a lot of numbers ranging from 58.1 all the way to 58.7. Well, for a lot of them, we see that I think most of you guys select 58.2, right? So if we are going to do an average of all your readings, it probably will be around 58.2 or 58.3, okay? But we cannot say that 58.1 is not correct or 58.7 is definitely not correct. Well, by looking at the picture here, I would say 58.7 might be a little bit off. But if you're writing any numbers between 58.1 to 58.4, I think all of them are reasonable, right? But you see that there is a random deviation from each other when you're reading it. And even for some of you, you try to correct your answer, right? You say, oh, the first time when I look at it, I think it's 58.1, but now I think it's 58.2, right? So what's the difference between these two types of errors? One is random, right? It could be also positive or negative from the average value. The other one is just one direction, and it's not because of the reading from different people or different triers of reading, right? So that's the difference between the two types arrows. The left one is systematic arrow, and the right one is random arrow. So what we can see here is associated for the systematic arrow is probably a building problem with the instrument. Like in this case, it probably means the pH meter is not well calculated. So it's not giving you an accurate reading. If you give an 8 for a pH 7 buffer solution, then if I ask you to do the measurement of water, you probably will also get a very high value, higher than 8, right? But we know water pH should be 7. So there's a systematic error in the measurement, and it's going one direction, right? If the instrument is giving higher values to solutions, then it will always give higher values to the solution. Versus the random error, when different students are reading the scale, they can get slightly different variation. And it could be positive or negative compared to the average value. In a word, it's very random. So that's the difference between those two. And if we go furthermore to discuss the difference between those two in a table, the systematic error is also called determinate error. So it's some error that can be determined and maybe calibrated by running a couple of experiment or calibration, versus random is indeterminate error. We know that it's the error coming from reading because the scale is not big enough, so it's hard to get accurate reading, and it's a random phenomenon. So if we look at the source again, as I said, the systematic error can come from a flaw in equipment, or it could be a design of an experiment. While random error is kind of uncontrolled variables. Okay? For the property of the two different types of errors, the systematic error is reproducible. So like I said, if the pH meter always gives you a higher reading of a buffer, then it will always give you a higher reading to other solutions. And it can be discovered and corrected. This is actually why we have to do calibration, right? So when we're using a pH meter, we realize that it doesn't give you accurate reading to the buffer solution, then we will have to do calibration with the instrument to make the value match the desired value, and then you use it for the unknown detection. Well, for random error, it has an equal chance of being positive or negative, and it cannot be corrected. So there is no way for us to get an absolutely accurate reading of a scale of a burette or a volumetric flask liquid level. So you can try your best to get as close as possible to the true value, but there's no way you can be 100% accurate, and there's no way to actually quantitatively measure that, right? And as a result, if you have a systematic error, it will deviate from the true value, which as a result will affect the accuracy. Well, for random error, because we know it's like kind of random, it could be either positive or negative, so it kind of makes a result or different measurements scattered out. So